Okay, Tony. Yeah, okay. Good afternoon, participants. I welcome you to this faculty development program. Yeah. Good afternoon to all the participants. Yeah. Very good evening to one and all present here. And thank you for joining us on this day 3 session of 7-day virtual faculty development program on contemporary amelioration in nanostructured materials conducted by the Department of Science and Humanities, Jeppiaar Engineering College. Share your knowledge. It's a way to achieve immortality. On behalf of the faculty members of our college, I, F. Regan Maria Sundarraj, Assistant Professor, feel immensely proud in welcoming our Admiral Chairman and Managing Director, Dr. M. Regina Jeppiaar Group of Institutions. Our familiar guest, Dr. V. Ganesh, our respectable Chairman, Principal, Dr. V. Nadarajan, our beloved Dean of Academics, Dr. Salisha A. Stanley. Today, FDP has come about more than 100 participants participating from across India, making this national program in spirit. I would like to announce today's topic is electrochemical biosensors for healthcare diagnostics. It is indeed a great honor and privilege to put forward the laurel and scientist of our chief guest of the day, Dr. V. Ganesh. Dr. V. Ganesh is currently working as a principal scientist at CSER, Central Electrochemical Research Institute, so called CSER Sikari, located in Karakkudi, Tamil Nadu, India. He completed his undergraduate and master degree in chemistry. Notably, he received gold medals for securing the first place in BSc and MSc as well. He pursued a PhD degree in chemistry under the guidance of Professor V. Lakshmi Narayanan, Raman Research Institute, RRI, Bangalore. He has completed his postdoctoral research at University of Edinburgh in Scotland, UK, for a period of 3 years, where his research work is mainly focused on biosensors, bioelectrochemistry, bioelectrocatalysts, and bioinorganic chemistry. Under visiting research fellowship, he carried out research work at University of Manitoba, Canada, where he worked on the area of nanomaterials for electrocatalysts, liquid crystals, and electrochemistry with application primarily focused on biology and catalysts. Overall, he has about 85 publications in internationally reputed journals and contributed 2 book chapters. He is the recipient of many prestigious awards like CSIR Young Scientist Award in Chemical Science, Pudhiya Thalaimurai Nambikai Natchathiram Award for Science and Technology, and SAEST Golden Jubilee Young Scientist Award, etc. He has delivered many invited lectures across India and in other countries like Japan, Canada, and UK. He has completed 9 sponsored projects and currently possesses 4 sponsored projects. His research interests mainly include electron transfer studies, electrocatalysts, self-assembled monolayers, microbiological fuel cells, scanning probe microscopy, catalysts, electroanalytical chemistry, nanomaterials, liquid crystals, biosensors, and bioenergy and graphene-based materials for biosensing, catalytic and supercapacitor applications. I'm sure our participants would be just as delighted as I am to be engaged in this session, presided by such an eminent scholar with the blessings of the Almighty and honorable founder of JPR institutions, Late Colonel Dr. Jeppiaar, I would like to hand over the session to Dr. V. Vignesh.
Thank you, sir, for your kind introduction.
Thank you.
So, good evening to all of you. Just give me a minute or two. I will load my presentation and we will start discussing. Okay?
Yeah, sure, sir. Sure, sir.
So, I hope I am audible. And,
yes, sir.
Right. And you guys could able to see the slides as well, I guess, right?
Yes, sir.
Yeah, okay. Okay, just give me a minute. I'll close this.
Yeah,
and
yeah, sure.
Okay. So once again, very good evening to all of you. At the outset, I would like to thank Sri Regan Raj, anyway, I can say Dr. Regan Raj, soon to be, for giving me an opportunity to be a part of this FDP program, faculty development program. I'm sure for the past 2 days, you all would have had a nice discussion. I hope I can maintain the similar enthusiasm. So today I'll be talking about electrochemical biosensors for healthcare diagnostics. And I do remember that I am talking to faculties, so and also from diverse fields. So what I'm going to do here is I will give you a very broad overview of what is happening in this field. And I will start with first where I come from and why do people involved in doing research. And slowly I get you into the field of electrochemical biosensors. Typically, classical book-based definition of what sensor is all about. Then a little bit of electrochemistry through maybe some stories. Then I will get back to my research, what I have done in this field for the past 10 years or so. Okay. Now, so I usually start from where do I come from, because on a very lighter note, one fine Sunday I went for a haircut at Karaikudi. As many of you know that Karaikudi is located in the southeast of Tamil Nadu, and it is a kind of town. So the barber asked me, where do you, sir, work? I said I work in Sikri. Of course, I did not say that I'm a scientist. I said I work in Sikri. Then spontaneously, barber asked me, "Do you guys make atom bombs?" I was very surprised. Then I asked in a typical Tamil slang, how long you are here in Sikri? Then he said he is here for about 30 years or so. Then from that moment onwards, I decided wherever I go, whatever I talk, my first slide would be where do I come from. So probably many of you would know what Sikri is all about, but I can only highlight the history behind it and the achievement Sikri made over the past 7 decades or so. Now, Sikri is profoundly known as Central Electrochemical Research Institute. It is one of the constituent laboratory of CSIR. We do have 3 different subunits. Of course, headquarters is located at Karaikudi. We have units at Chennai, Mandapam and Tuticorin. We are roughly about 400 employees, out of which 1/3 are scientists. And we do work at looking at fundamental aspects of electron transfer reactions across electrode-electrolyte interface to material design for modulating such electron transfer reaction to bring in application in many different fields. I would say that it's a multivarious application. And we do develop a small instrument or device for target-based approaches. So if you look at the history behind it, the foundation stone was laid in the year 1948 by then Prime Minister Sri Pandit Jawaharlal Nehru ji, and it was declared open in the year 1953 by then President Sri Sarvapalli Radhakrishnan. And he is just a person who is standing next right to him is Dr. Bhatnagar. He is the founder of CSIR. and the person peaking between the two is Dr. R.M. Jeppiaar. He is the greatest philanthropist known from this part of Tamil Nadu. In fact, he has donated 100 acres of land and 15 lakhs of rupees in 1953 itself to establish such an institute. Now, why I stress upon this scenario is because even now, SICRI is the one and only research institute in India completely devoted to the field of electrochemical science and technology. A research institute completely devoted to the field of electrochemical science and technology. We are roughly about 7 decades old, okay, and the contribution both to the nation building ion selective electrodes for Na plus K plus ions were also developed by SICRIans. Okay, I can keep on listing down like this to the latest addition being Make in India product of developing 100 unit cell of lithium ion batteries, which is recently established in Chennai unit. Okay, now during the inaugural function, this person was there. Of course, you all know who he is. He is Sir C.V. Raman. And during the inaugural function, he asked such a question: what are these laboratories going to do? Unless otherwise, the feel that it is up to them to do their best. Otherwise, these laboratories will remain as a giant question mark in the sky. Of course, he was a well-known physicist. So he was looking at the sky. So he posed such a question. I'm sure if Raman would have been alive today, he would have been more than happy to see what SICRI has done over the past 7 decades or so. But he is such a eminent personality and he was a very outspoken person. He never mind what it is all about. Now, this is just to propagate the importance of Nobel Prize. Okay. Now we do celebrate Science Day on every year, 28th February, in order to commemorate the discovery of Raman effect. Okay. For that discovery, Raman got Nobel Prize in Physics in 1930. I'm sure you guys would remember what Nobel Prize is all about. Nobel Prize is awarded to 6 different fields, right? Physics, chemistry, physiology or medicine, economics, literature, and peace. So every year during second week of October, the Nobel Prize awardees will be announced, and during December 10th, the award ceremony will happen in a place called Stockholm in Norway, except Nobel Prize for Peace, which will happen in a place called Oslo in Norway. The first one is Stockholm in Sweden. The Nobel Prize for Peace is Oslo in Norway. Okay. So why I stress upon Raman is because even now, Raman was the one and only scientist who got Nobel Prize for the work he has done completely in India. I'm sure you guys would know that there are many other Nobel laureates from India in many different fields. I will show you that slide maybe in a minute or two. But if you look at scientific perspective, Raman, again I repeat the sentence, Raman was the one and only scientist who got Nobel Prize for the work he has done completely in India. And when he announced the discovery of Raman effect, he has performed that experiment with the quartz spectrograph, and he demonstrated in a famous lecture in Bangalore during March 16, 1928. Okay. And of course, these are all the Nobel Prize winners from India. As you can see, Rabindranath Tagore was the first Indian to get Nobel Prize in the field of literature. And Sir C.V. Raman, according to Nobel Prize website, was the first non-white scientist to get a Nobel Prize in Physics in 1930. So we have many Nobel laureates like Hargovind Khurana, Chandrasekhar, Amartya Sen, Venkatraman Ramakrishnan, Kailash Satyarthi, to the recent addition being Abhijit Banerjee, etc. If you look at their work, especially from the science perspective, most of them work abroad, but even now, as a proud Indian, we claim those NRIs are also Indians. Okay. Now, why I talk about Nobel Prize is because, of course, we are the flag bearers of such kind of Nobel Prize winners. By using such kind of ideology, we can in fact motivate the student to pursue science as their career, so that there is ample amount of opportunity available to execute such kind of research. Of course, thanks to Regan, he was reading my biodata. Basically, I'm a chemist. My bread and butter is on electrochemistry. I do take concepts a little bit from material science and biology to come up with sensors and devices, mainly for energy and environmental applications and for biomedical applications. Okay. So as far as today's talk is concerned, what I do is I will talk about why do people involved in doing research and why understanding electron transfer reaction is important, and how do you modulate such electron transfer behavior to come up with applications in the field of sensor, catalysis, energy storage and conversion devices, etc. And what effect by introducing the nanomaterials one would get. Okay, I'll try to highlight those points during the course of my lecture. Now, why do people involved in doing research is because for this issues. Now, it's not like, just because we got some job, we need to do research and, publish papers to get our promotion, etc. In fact, here I listed down the humanities top 10 problems, which of course we will face in the upcoming 50 years or so, starting from energy, water, food, environment, poverty, terrorism, war, disease, education, democracy, population, etc. I can give examples for each of these fields that it is going to be a big problem. Let's take, for example, energy, right? You guys remember about maybe 4 or 5 years ago, in Tamil Nadu alone, we had about 14 to 15 hours of power cut, right? I think it was 2014 or 15. Remember, we had 14-15 hours of power cut. Remember, we have only 24 hours a day. And what will you do with free mixie, grinder, etc.? That's part of the story. But in addition to this, India is digitalized. We move from classical blackboard-based teaching to virtual online mode of teaching. Everyone uses now laptop, mobile phone, computers, etc. for conducting the classes, conducting webinar, even doing research experiments. There are labs, they are involved in doing research experiments online. Now, in that scenario, energy becomes very, very critical. You need, power backup. We need batteries, supercaps, or fuel cells, etc. Right? Apart from this, you remember, I think previous power minister for power source, which is Mr. Piyush Goyal, he mentioned that by 2030, all the vehicles in India would be EV, electric vehicles. So how are you going to develop all these things, right? That's the question which is there in front of us now. Like this, I can give example. Since I am going to talk about biosensor, let me take an example of a disease. Given a current situation, really, I don't have to talk about the disease, which is very visible to us. As you can see, maybe I'm roughly about 40 years old. When I was a kid, when I get a fever, my father used to take me to a single doctor. Okay, the doctor would give me an injection or a tonic, and next day I would be, feeling better. I take my bat and start playing cricket when I was a kid, and now we can start doing our regular activities. But if you go to a doctor today, let's say with a headache, what are the kind of initial questions they would ask? Sir, why don't you take an ECG and see, how your heart works? And did you check your blood glucose level? Did you check your sugar? These are the questions normally people ask. Remember, I'm not here to criticize anything. I'm here to just push you the problems we face and how do you find solution to this, right? Now, apart from this, in 2012, the human population across the globe was estimated to be 6 billion. And it is expected to grow roughly by twice by 2050. So how are you going to accommodate all these people in the globe and providing them green energy, good drinking water, clean environment to live? So how do we make progress to this? And the only way you can find solution to all these problems is through science and technology, is through research. I can go even one step ahead and say that electrochemistry can offer solutions to all these problems. Okay, I will highlight this point again during the course of my lecture. Now, if you start finding solutions through research and through science and technology and research-based approach, we can make a little bit step towards self-reliant India. That's the dream our Honorable Prime Minister Sri Narendra Modi ji is dreaming of now, and which will come into reality if we start finding solution to all this problem. Now, there are two things right now which is prevailing as a much problematic in the current society. The first one is healthcare, and the other one is energy sector. I'm not going to talk about energy today, but let me restrict myself with healthcare alone. Okay. As we know, there are many diseases present in our society. Again, when we were kid, there are no diseases called. Let's say when we were kid, maybe it was just chikungunya. It was just chickenpox and maybe malaria. But now you see how many diseases we have. We have Ebola, we have Nipah. I don't know. Keep on going right up to this Corona now. So how do you find solution to all this problem? If you want to find a scientific solution, you need to basically identify the root cause for this disease, and you understand the chemistry bio problem. I'll talk about this chem bio interface in a minute. And you investigate what's the bioorganism involved in this. Then you come up with a target-based approach for a diagnostic tool. You testify your hypothesis so that you can come up with ultimately health diagnostics for providing a cure for such disease. So how do you again give? It's only through science and technology. Now, I mentioned in the last slide that understanding chem-bio interface becomes very critical, right? Let me ask you guys a series of questions. You don't have to answer, just think about it, okay? Now, after a good food for dinner, we all go to bed and sleep aramse, and we wake up in the morning. Who asked you to wake up in the morning? Maybe through alarm, phone call, disturbance from wife, husband, girlfriend, boyfriend, whatever it is. We woke up, and maybe we get ready in an hour or two. After that, you feel hungry, right? So why do we feel hungry? Let's assume we take some good breakfast, and after that, of course, we go to a bus stop to catch a bus to go to university. Of course, now buses are not running. Okay, no problem. Just assume that you take a bus to go to university, and when you look at someone, you feel very happy, and when you look at someone else, you feel very much irritated, right? So we express our emotions during the course of time. Why do all these things happen? A broad answer would be all these things happen because of biochemical reactions which occur in our body. I would go one step ahead and say that all these things happen because of electrochemical reactions which occur in our body. When I say biomolecules undergo reduction, some molecules would undergo oxidation, some would undergo reduction. So there is a redox reaction which is established at this interface. Okay. Apart from this, there are electron transport chain which communicates with cells among cells which present in our human body and provides information. So in order to understand such behavior, very, very complicated system, we need to understand how chemistry bio interface work. Okay. I used to tell this in a joke when I teach classes, like, when someone plays any game, and during the sports, normally what do? During the break, we take glucose, right? So I was giving lecture like this in a college. Then I asked the students, so Thambi, during the break, what do you guys take? And one fellow stood up and said, we take rest, sir. And of course, that was a good answer. Then I told, yes, during the break, we do take glucose. So why do we take glucose? Because the moment you consume glucose completely undergoes oxidation to give you 6 CO2 plus 12 H2O plus energy. That is a classical book-based equation, what we would have studied in school days. So it gives a spontaneous energy because delta G of that reaction is negative, gives free energy of the reaction is negative. Now, and another example for understanding this chem-bio interface is, there is a glucometer which is available in the market. Probably you guys would have heard about it, right? So what do? In order to check the amount of glucose present in our blood sample, we prick our finger, take a drop of blood, put it on a disposable strip, and you insert that strip into a device to measure how much glucose is there. How that instrument works? Well, the flexible and disposable strip has an enzyme called glucose oxidase, which specifically oxidizes glucose to gluconic acid and hydrogen peroxide. The moment you insert that strip into a device, the device, using electrochemistry, it can either oxidize or reduce hydrogen peroxide, and in turn will measure how much current is produced during this reaction, and you can able to measure how much hydrogen peroxide is produced. In turn, you can correlate how much glucose is there in your blood serum sample through the enzymatic reaction. In fact, that's how the instrument works. That instrument is developed, which is a typical example of a device developed based on a multidisciplinary approach. So that's why understanding chem-bio interface becomes very, very critical. Now, let me tell you maybe in a minute or two for the classical book-based definition of what sensor is all about. Sensor is nothing but a device which converts either physical or chemical parameter into a measurable electrical signal. Okay. In general, it comprises of a sensing element, that is nothing but your enzyme, the glucometer, what I talked a while ago, and transducer, which is nothing but your electronic interface, which picks up the changes occurred due to enzymatic reaction, and the connected electronics will give you electrical output based signal. This is a diagrammatic flow chart of a chemical sensor. As I mentioned, the analyte which contains the target species, we can pass through the filter in order for the recognition site to pick up those analyte very specifically. So the transducer will pick up the changes, like it can measure ionic change, it can measure electron transfer rate constant, it can measure change in temperature, it can also measure change in intensity of light or polarization of light, etc. So the transducer will pick up those changes and convert into a measurable electrical signal through electronics. And in case of electrochemical signal, the analyte can interact either chemically or electrochemically with the transducer, but the produced signal is monitored purely using electrochemical technique. Okay, I will highlight a little bit about electrochemistry in a minute or two. Now, depends upon what is the parameter you measure. You can develop a sensor using a very, very simple techniques. Potentiometry, for example, you can directly measure the difference in potential and correlate with the concentration of the analyte. On the other hand, you can measure change in current at a fixed potential like amperometry, and the measured change in current can be directly correlated with the concentration of the analyte. In fact, the glucometer which is available in the market works based on the principle of amperometry. Now, apart from this, you can also measure either change in resistance or impedance or conductance and correlate with the concentration of the analyte too. Those techniques are called conductometry, impedometry, etc. These are all some of the characteristics a sensor should have. The sensor should be selective, and we can use a very, very small amount of analyte or volume to measure a target species, and it becomes handy if the device comes as disposable, reusable, and renewable. Okay, the response time should be quick, and it can have a reproducibility, etc. In case of biosensor, we can use enzyme, antibody, microorganism, or cell even as a molecularly recognizing element. and we can pick up the changes. As I mentioned earlier, it can bring about change in pH, or change in temperature, change in light, or even change in mass, etc. Depends upon the parameter we measure. The transducer signal is different. Correspondingly, we can term that as a different technique. But ultimately, what we measure is an electrical signal which comes out of this transducer. Now, I hope I am audible, right? It's not like I'm monotonously talking and you guys are listening. I hope so. Correct? Now, let me highlight a brief concept about electrochemistry. Since I'm going to talk about electrochemical biosensor, let me tell you what is the importance of this electrochemistry is all about. I mentioned earlier that understanding electron transfer is very, very important, right? Now, a study which deals with such kind of investigating electron transfer process at the interface is nothing but your electrochemistry. That interface could be solid liquid gas, etc. In general, electrochemistry deals with two different kinds of reaction. One in which you can apply an voltage to drive a chemical reaction, and in the other case where voltage is generated because of inbuilt chemical reaction. Let me see. For example, in the second case where voltage is generated because of a chemical reaction, the typical example is nothing but your battery. Let's say suppose we have wall clock in our house. The moment clock stops, what do? We simply replace a battery. Because of the inbuilt redox reaction with the battery, it provides an voltage output, and which is used to drive a clock, right? So that is a kind of category where the inbuilt redox reaction provides voltage. On the other hand, the second category where the voltage is applied to drive a chemical reaction, the typical example could be fuel cell. Probably you guys would have read in newspaper that we can use water as a fuel to drive vehicle. Can we really use water as a fuel to drive vehicle? Thermodynamically, water splitting into hydrogen and oxygen is not allowed, but you can tune the kinetics of that reaction just by applying a voltage of 1.23 volt. We can split water into hydrogen and oxygen. Hydrogen evolves at cathode, oxygen evolves at anode, so that both could be used as a fuel. Okay, so that is the case where one can apply the voltage and drive a chemical reaction. These are the general category what electrochemistry deals with. Now, I mentioned electrochemistry is a powerful technique to monitor reaction. Why? Because the moment any conducting rod into an electrolyte, there is a spontaneous formation of double layer at the interface, which establishes the layer of separation of charges at this interface. I'm sure you guys would know about this. This leads to a parameter called capacitance, and that is correlated with C is equal to Q by E. So that's the reason precisely the potential originates from. Now, the typical thickness of this interface is of the order of nanometer. And even if you apply 100 millivolt to this small distance, very, very tiny distance, the electric field felt at this interface is very huge. Okay, how do we calculate the electric field? Applied voltage divided by distance of separation. So 100 millivolt within a nanometer separation, which gives you into 10 power 6 volt per meter, 100 million volt per meter. Imagine, although you apply a very small voltage of 100 millivolt, the electrode-electrolyte interface will feel as if it is 100 million volt per meter. That's why many reactions which are not possible through normal chemical route, we can carry out those reactions using electrochemistry. That's why this techniques becomes much, much powerful one. Now, so normally we use three different electrodes in electrochemistry: reference, working, and counter electrode. The applied potential will flow between reference and working, and the resultant current will flow between working and counter. Now, where does the current come from? Okay, Recall Lee-Chatelier principle. What do I mean by Lee-Chatelier principle? If the system is at equilibrium, when you apply a stress, the equilibrium will shift in such a way that it will nullify the stress. Okay, it will get rid of the stress. Now, why do I worry about equilibrium? I again used to tell a small story. I think we have time for it, no problem. Maybe I'll take a minute and say, let's say, suppose if a person get an award or a medal or something, okay, the person goes up to the stage, receives the award, comes to the other side of the stage. Suddenly, some of his or her friends go and talk to that person. How many of you guys feel that that person would exhibit his or her real characteristic at that moment? The answer would be 99% no. Since at that moment, that person would be in the excited state, he or she would feel that probably that person is the one and only person in the world at that moment, would think that he knows the subject very well. Okay. But on the other hand, suppose let's say that student comes to a class very regularly. He or she may be very obedient, very punctual, again, good friendly nature, helping tendency, etc. All those real characteristics will be exhibited when the system is at equilibrium. Similarly, this electrode-electrolyte interface at equilibrium will exhibit its real characteristic. That's why it becomes very important to understand the system at equilibrium, near to equilibrium, and far away from equilibrium. Unfortunately, electrochemistry provides opportunity to understand system at all these phases. That's why it becomes very, very powerful technique. Okay, maybe another one more important point, then I will get back to my research, right? So for example, this is a very general schematic overview of what are the processes which involve in electrochemistry. Let's say you dip an electrode into a solution which contains a redox species. What are the steps by which an electron transfer reaction occurred? The molecules would diffuse from the bulk to the interface, get adsorbed on the electrode surface, undergoes electron transfer reaction. It can either donate an electron to the electrode or it can accept an electron from the electrode surface. So undergoes electron transfer reaction to give you a product. The product has to desorb and diffuse back to the bulk of the solution. Among these processes, whichever process is slower is called a rate determinant step. And usually diffusion of ions from the bulk to the interface is slower, and that's why we get a typical peak-shaped voltammogram in cyclic voltammetry, etc. Now, so I mentioned that electrochemistry plays a role through which one can even tune delta G from a positive to negative. Recall two different kinds of reaction what electrochemistry deals with. One which is a spontaneous, like battery for example, delta G is negative, and the other case where water splitting reaction, delta G is positive, which meaning non-spontaneous reaction, but you can apply a potential, okay, so that you can tune delta G from a non-spontaneous to spontaneous and vice versa. For a given process, both N and F are constant, so that the only variable parameter is E. The moment you change E, you can change the delta G. Okay, so that's why electrochemistry becomes much powerful. I mentioned that current comes from the Lee-Chatelier principle of perturbing the equilibrium. Now, these are the different modes of mass transfer through which current is being produced: migration, diffusion, and convection. Among these processes, all the equations in electrochemistry are derived based on the assumption that diffusion is the predominant mode of mass transfer. Now, I mentioned that it is important to understand the system at equilibrium, near to equilibrium, and far away from equilibrium. And this is the equation which provides relationship between current and potential under all those conditions. In fact, it covers the entire range of spectra, starting from Tafel polarization to impedance to polarization, voltammetry, etc. I'm not going into detail of it, but just to give a flavor of what electrochemistry is all about, This is the equation which provides relationship between current and potential under all given conditions. Now, we can use different techniques in electrochemistry. We can use both 2 electrodes and 3 electrode system. We can carry out equilibrium technique, a simple measurement of potential or capacitance with the time or concentration, or we can use transient techniques like changing the time domain, like voltammetry, pulse techniques, etc. And the other category is steady state techniques where impedance spectroscopy comes into picture. Okay. Now, since of course I'm going to talk a little bit about nanomaterials in the field of research as well, in the field of biosensor especially. This is a typical band-based diagram where you can see that if you keep on reducing the size of this nanoparticle, the energy levels are quantized. Okay, if you keep on reducing the size of the element, you would get into the regime where the energy levels are quantized, so that you would get a discrete energy level for a given molecule. And even if you go further to reduce the size, you would end up with a very smaller tiny particle called quantum dots. Of course, a major feature of this quantum dot is the quantum confinement effect. Okay, the energy levels are quantized and discrete, where the size of the quantum dots are smaller than the Bohr's exciton radius. Okay, so that's why such tiny particles are called quantum dots. So what are the advantages? Well, the properties are drastically different compared to the bulk one. Since you establish a prescribed energy band gap between the conduction and valence band, you can bring in many exciting properties in terms of light absorption and emission, fluorescence, phosphorescence. And apart from this, you can also create many surface defects. Physics would call that as doping, and chemistry, would call that as impurities in some cases. But if we look at the band level energy based diagram, we create many surface trap state by which you can absorb light at different wavelength and emit in a completely different wavelength. Okay. Now, getting back to research, what I worked on, maybe another 20 minutes or so, I'll talk about what I did in the field of biosensor. Now, I started my career, of course, with the self-assembled monolayer, which is very easy to form. This indicates formation of a single layer of molecule on a solid surface by a spontaneous chemisorption. As you can see, it can induce a high degree of ordering and orientation of molecule on the surface, and which can provide pre-organized surface. What's the advantages? Well, it forms an appropriate framework to investigate the electron transfer reaction across the interface. You can see from this molecule, for a given length, the aromatic molecule mediate electron transfer reaction roughly about 100 times faster than the similar length with aliphatic chain. As we know, the aromatic moiety has a delocalized pi electrons that can provide more electron transfer, act as an electron shuttler across this interface. Not only that, you can also create a biomimic catalysis on the surface. Okay, here we demonstrated a cytochrome C oxidase model where oxygen reduction to water using an enzyme could be mimicked on the surface. Okay, now keeping this in mind, what we have done is we designed a molecule in such a way that we have a surface binding domain, we have an electron transfer spacer regime, and we have a metal binding domain on top of this molecule. In addition to that, we can enhance the binding of the analyte by introducing a hydrogen bonding unit. Okay, so that the moment you dip this onto an electrode surface, these molecules self-assemble on the surface of the electrode, and by adding metal complexes like in terms of copper, zinc, etc., one can tune the electron transfer reaction. So, for example, in this case specifically, we observed that copper system mediates electron transfer roughly about 600-fold higher than the corresponding one without any metal. Okay, so of course we come up with a novel concept called metal mediated electron transfer reaction. Why do I talk about that? Well, we have a system where if we don't have any metal, there is no electron transfer reaction across the interface. The moment you introduce a metal like copper, we do have an electron transfer, so that you can throw in some anions which can specifically go and bind to copper or remove copper from the system, so that you can develop a sensor. And you can monitor the binding event by looking at how the electron transfer rate constant changes, or by measuring a parameter called charge transfer resistance from impedance spectroscopy. As you can see that among the many different analyte we added, only cyanide introduces visible change in the output of impedance spectroscopy. Thereby you can bring in the selectivity of the cyanide sensor. Now, not just metal, you can also use many different molecules in a variety of systems, so that once you tune this electron transfer across the interface, we can even mimic, understand the enzymatic kinetics, etc. And during the course of reaction, we introduced a different nanostructured material, like in terms of gold nanoparticle, nanostars, graphene quantum dots, etc. Now, among these nanostructured material, I would try to highlight very specifically about this gold nanostar, because this is a unique morphology one would get, which is how do I put it? Which is a kind of very easy to prepare. You mix a surfactant with water. We do know that depends upon the concentration of these two systems, one can go from a micelle, reverse micelle to hexagonal liquid crystalline phase, etc. I hope you guys know about what liquid crystals are all about. Liquid crystal, in contrast to solid, you define that by a 3D arrangement of unit cell, so which has both position and orientation. But in the case of liquid crystal, okay, it has a long range orientational order and there is no positional order, meaning it is a kind of in between liquid and solid state. But as far as we are concerned, which is a very good system, since liquid crystal forms such kind of hexagonal pattern, you can control the aqueous domain. Okay, the remaining part are surfactant long hydrocarbon chain, so which is a hydrophobic moiety. You can control the aqueous domain so that you can carry out the reaction only in that domain, right? So by playing with the concentration of this, we come up with, as you can see, different nano-structured material in terms of star shape. One can tune the length of this arm and core of this star, etc. And depends upon the sharpness and length of this, we can also extrapolate this to ACRS application, surface enhanced Raman scattering. Okay, so using such kind of technique, we come up with many enzymatic sensor. Among the several sensor what we develop, we come up with a very important sensor for this lipopolysaccharide. Why this molecule is important is because it provides information about human immune response system. In general, mammalian immune response system. Let's say, suppose a person met with an accident, God's grace, we take them to ICU, and whether a patient would survive or not would be decided by looking at how this molecule behave. Okay, so initially it leads to organ failure, and ultimately it leads to what is called a septic shock, a self-poisoning of the body. But if you look at the structure of this molecule, it is a kind of different patterns. We have long hydrocarbon chain, sugar moieties. Okay, these are sugar moieties. And apart from this, we have surface functional groups to target. Okay, this molecule is toxic because of higher negative charges associated on top of this molecule. So what we did is, we come up with a good strategy where by using hydrophobic interaction, you can anchor this molecule on the electrode surface, hydrophobic interaction. And we added receptor for each of the components. Like there are sugar binding protein called lectins, which will bind and neutralize the charge. Similarly, you can develop complexes which are very specific to phosphate binding. Okay, since this involves a charge-based interaction, we can monitor the binding event by measuring impedance, a very simple approach. Okay, so in a way, what we come up is with a complementary pattern-based recognition receptor. As you can recall from the structure, it is like a different structural patterns, and they are complementary to each other. And we created receptor for each of these components, and so that you can monitor the binding event. Now, how are we coping up with time? Yeah, maybe I will take about 10 minutes or so. Is it okay, Regan?
Okay, sir. Okay, please
yeah.
go ahead. Please go ahead.
Yeah, maybe 10 minutes and then I will wind up my talk. This is another, so the first part of my research is a kind of molecule what we developed, and the next example was the methodology what we developed, and the third one is about the sensing platform. Okay, so nowadays we moved from I was highlighting classical blackboard based teaching to PPT online mode of teaching. But in between these two, when I was doing my masters, I remember my teachers used to take classes using an overhead projector sheet, okay, which is nothing but a flexible plastic sheets. Even we give seminars using such kind of sheets. So what we did is we basically employed a simple electrochemical technique like electrodeposition, and we made them as a sensor strip. So we deposited copper, nickel, etc. Of course, we chemically functionalized those flexible strip and demonstrated those strip as a typical strip for sensing glucose from blood serum. Okay, these are all typical amperometry based graph. As you can see, depends upon the concentration of the analyte, the current would vary, and different analyte, the sensor strip is very specific to glucose alone. A slight modification in the functionalizing strategy, we form a monolayer and over which we deposited silver, and followed by we deposited zinc oxide, so that we can use such kind of chemically functionalized strip for pesticide detection. We come up with a pesticide sensor for methyl parathion, okay, because this moiety would go and bind to zinc oxide very preferentially, which has a strong binding affinity. You can monitor the binding event using a voltammetry technique. Simply measure change in current with respect to change in concentration. And we validated such sensor using complementary technique like Raman. Now, among the many different techniques what I talked about, many different nanostructured material what we introduce, we come up with a simple method to prepare different size tunable and different light emitting graphene quantum dots. It's like a simple electrolysis. Okay, you take a carbon rod, you keep another cathode, you dip them in an electrolyte. So do a electrolysis process, simply apply a constant current, for example, galvanostatic method, and depends upon the time duration of the electrolysis and followed by the nature of reducing agent like hydrazine, sodium borohydride, or even some organic moiety you can add as a reducing agent. You would get a supernatant and a precipitate, and depends upon the nature of reducing agent and the time duration of electrolysis, you would get a different light emitting graphene quantum dots. Okay, and the settled precipitate is nothing but your reduced graphene oxide. So that of course we went on and characterized the structural characteristic. You can see that the quantum yield is quite good. For different colors we obtained up to 30% of quantum yield. Okay, so those light emitting graphene quantum dots we used for bioimaging application, specifically for imaging E. coli in this case, and the settled precipitate, which is nothing but reduced graphene oxide, that we analyzed using Raman later. We employed them as a supercapacitor for as a charge storage system. Okay, so like this we developed many systems using enzyme itself as a reducing agent to get fluorescent gold nanoparticle. Not only the reduction in size, but also you can use them to emit different colors. In this case, it is yellowish green fluorescence, so that we can develop a multimodal approach to sense glucose. As an example, we demonstrated colorimetric, fluorescence based, apart from the regular electrochemical. Okay, of course, not only the enzyme based, you can also change the pH of the solution so that you would get into different emission. For example, in case of acidic, the system would emit a rosy red fluorescence, and when you change the pH to alkaline, it emits the green. So using this strategy, we come up with a sensor for an amino acid called cysteine. You can see, which is very, very specific. Okay. Right. So maybe another 5 minutes. This is a kind of slightly different field, but it is okay. So in this series, we are also involved in developing this microbial fuel cell, which is very important. You know, normal fuel cell, we use an anode and cathode. You can generate the power output by oxidizing the fuel at anode. In case of microbial fuel cell, instead of catalyst based anode, what we do is we grow microbes in the anode chamber, so that depends upon the microbe you grow, you can able to get the power output. You can generate power from, let's say, food waste, industrial waste, even wastewater, etc. As you can see, depends upon a meaningful wealth from waste, so that you would get the power of the order of microwatt to milliwatt. That is sufficient enough for a small power required devices. Okay, glowing an LED, etc. These are some of the MFCs, I mean microbial fuel cell configurations, what we developed in our lab. Now probably I will end my talk with this set of experiment, maybe a couple of minutes or so. When I was talking about this OHP based sensor strip, okay, we developed a sensor for detecting a single analyte. But you can create a pattern on this flexible strip so that individual array could be used to address a single analyte. By using such kind of array based electrode, we can address simultaneously different analyte. We can develop a sensing platform for multi-analyte detection. Why this is important? Well, now what we are currently working on is, we are working on a non-invasive mode of detection. Okay, recall the glucometer, what I talked about in the very beginning of my lecture. You need to prick your finger, take a drop of blood, and analyze the system. Rather, we can even analyze healthcare of a person from sweat itself. The scientific term for sweat is called perspiration. You know, probably again, there are two conditions under which a person would sweat. One, thermal difference, temperature difference. The other one is the emotional changes. If suddenly someone comes and proposes to you, you know, some people start sweating. Or in case of students, when they start going and attending interview, or you know, suddenly a teacher comes and announces there is an exam today, then the students would start sweating. You know, but if you analyze the constituents of the sweat, there are many different biomarkers, starting from glucose, lactate, urea, Na+, K+, chloride, etc. In fact, analyzing these analyte would provide information about the human health condition. And that's why nowadays, you know, people started using this smartwatch, looking at a pressure and how many steps one would have, one has to walk today, etc. All these things developed based on such flexible sensing based platform. Once we are through with such kind of sensor devices, we can even apply this in the field of sports and defense arena. Okay, so for example, in sports, I can give an example. We do watch Olympics, right? Suppose, let's say we give a 100-meter race. How do we find out whether a person has taken a drug or not? We blood sample before the start of the race and after the completion of the 100-meter race. So people levels of like adrenaline, many other biomarkers, and normally this takes roughly about 3-4 years. By the time that person would have got already many sponsorship, he would have earned many 2-3 years. You say that you have been tested positive, so we strip off your gold medal. What is the use? He would be happy to remove the medal and give it to you. So that's not a good scenario. What we need to do is we need to monitor runs itself. By using a biocomputing approach, one can do that. A similar concept could also be extended to defense application as well. Now, finally, to conclude, electrochemistry in conjunction with material chemistry and biology can provide solutions to global issues, what I talked about. Of course, today I restricted myself to healthcare diagnostic. So mainly in the case of sensor, and you can tune the sensor parameters by introducing nanostructured materials as well to ultimately come up with smart materials and smart sensing. What do I mean by this smart material and smart sensing? Well, you guys may be listening to me. What this guy Ganesh talks about, starting from global issues, Nobel Prize, RCV Raman, electrochemistry, sensor, etc. You get bored of it and slowly lean on your chair, and the chair understands that you are not interested, so it converts into a sofa so that you can sleep aramse. That's the kind of smart material we talk about. But remember, it can also act as a smart sensing. The chair can prick you and say that, see, he is providing a lot of ideas for you to develop. Probably it could help you in the future. So the moment it prick, you just wake up and listening to me. That's the kind of smart sensing. Of course, few of the concepts are already. Let's say if you start a two-wheeler, the moment you touch your accelerator, the speedometer would display saying that, Ganesh, welcome. Today your blood pressure is this much, your glucose level is this much, you are allowed to drive. Such kind of scenario would come. To do all this, we need multidisciplinary group effort. Not just chemists, not just physicists, not just biologists alone would do it. We need to work in tandem. We need to work together as a multidisciplinary approach to come up with the solutions for all these global issues. So finally, again, I thank the organizers, so especially Regan sir, for providing an opportunity for me to share with you my opinion and what I learned during the course of time. And also, I am thankful to the organizers, all the administrative staff of Jeppiaar College. And final thanks go to all the participants, probably who all would have listened patiently for the past 1 hour or so. I would be very happy to answer any queries. Thank you. Thank you very much.
Thank you, Ganesh sir, for your informative talk. I would like to say
and we take the concepts and work. It's not like that. In fact, there are, I did not highlight, since it's not just about electrochemistry, there are fundamental contributions which come from Indians too. There was a fourth model of electrical double layer, which many books do not talk about, which was proposed by a Sikrian. Those days in 1960s, there was a Sri Lankan Tamil called Devanathan, who was working with the famous electrochemist. His name is Bakris, and even it was called Bakris Devanathan model. Not just that, even in the case of liquid crystal, there is a different kind of liquid crystal called discotic liquid crystal. That was also discovered by Indians. But we have a feeling that we don't contribute to the field of science. I want to break that barrier and say that in fact we do contribute to fundamental aspect. And once you understand the fundamental aspect, it is easy to extrapolate to application point of view. For example, why I talked about this tuning electron transfer reaction is because the moment you tune or modulate such electron transfer reaction, it is easy to show the applications in the field of sensor, in the field of catalysis, and energy storage or conversion devices, which is very easy. So that's why I started with some fundamental concepts and slowly get into the application point of view. If you look at from the business point of view, yes, I want to, let's say, fabricate some 10 sensors. I don't worry about the mechanism behind sensing or such fundamental concept. What I want is a ready-made device I can use directly for the business. That's the kind of business point of view. I think from the research perspective, we need to have a compromise between the two, and we need to not compromise on fundamental to look at only from business point of view. We need to have a balance of both, and unless otherwise you do research, you will not come up with a device at the end of the day. So it is very important that we need to understand both. I hope I answered
Yeah.
my
Yeah. Okay. Okay, sir. Sir, we'll straight away go into the question that is raised by the participants, sir. First question is how to prepare protein-based electrochemical biosensors from bacteria.
Okay. So there are many different interaction one can use. If you want to detect bacteria, let's say there are approaches one can adopt, like both structure based and function based. In the case of LPS, what I showed as a sensor in our work, the sensor works based on the structural components. I showed a long hydrocarbon chain, sugar moiety, functional groups, etc. So that when you add a receptor or binding analyte to this molecule, which will go and bind to specific component of the structure, so that you can monitor the binding event by looking at changes in electrochemical or electrical signal. This is one approach. The other approach is to develop sensor based on function. You can develop a sensor for, let's say, if it is for enzymatic reaction, you monitor glucose oxidase, which converts glucose to hydrogen peroxide, so that you measure how much hydrogen peroxide is produced. You can develop a sensor for hydrogen peroxide and correlate with the glucose, for example. Hydrogen peroxide is one of the good biomarker you can use for analyzing many different diseases. Okay, so such kind of function-based approach also one can do. Apart from this, there are methods like antigen-antibody interaction, nucleic acid based interaction, or DNA binding based interaction one can monitor to develop sensor. So these are the many different approaches one can employ to develop sensor.
Yeah. Okay, sir. Second question is there a field example of cyanide phytoremediation in gold mining wastewater?
Good. Yes, good. In fact, since we are from Electrochemical Research Institute, I think that person may be, really clever, I guess. During the electroplating, we always use gold cyanide salt in order to deposit gold on the electrode surface. Okay. So when we discard such kind of electrolyte after the deposition, always cyanide leaching would be there. Okay, which is, of course, the allowed level of cyanide according to WHO, World Health level, is of the order of ppm level. So till that point of time, it is allowed to be in the drinking water, but beyond which it causes really death at the end of the day. Now it becomes very critical to analyze how much cyanide is there in such kind of water. And in case of gold mining, it depends on what kind of salt we extract from. Okay, so depends on that. There could also be a possibility that cyanide device what we used a while ago in the maybe 5 years back or 10 years back, people reused that CDs to, there is a thin layer of gold coated on back of the CD as well. So yes, there could be a possibility that even cyanide is present there in gold mining as well. So that, see, I can translate a similar methodology onto a strip so that the moment you dip that strip itself, we can develop a color-based sensing or even electrochemistry-based sensing for detecting those cyanide ions. Yes, there is
Yeah,
a
third
possibility.
question. Thank you, sir. Third question is, can we consider quantum dot a high energy particle as high energy particle?
Yeah. Okay. It depends on nature of the level one would get depends on the material. Absorption and emission could occur at a different wavelength. When I say at different wavelength, by tuning the size, you can get into E is equal to h nu h c by lambda, that formula. If you go to a very high wavelength, you can able to get the low energy particle. And if we go to a very smaller wavelength regime, like a very smaller wavelength regime, you can get a high energy particle. Yes, in principle, by having said that, we are not going to get kilograms of hydrogen or oxygen from water splitting. It would always end up with micromoles per level to millimoles. Okay, that we have to keep that in mind.
Thank
Yeah.
you, sir. Thank you.
I
Thank you
hope
so much, sir.
I answered.
And
Yeah.
there are some more questions next meeting, sir. It's almost time.
Sure.
And
Okay.
one anonymous question is feedback link. Send feedback link. Feedback link is going on, sir. Okay, sir. So, and this is an example of this program is an example of like a national program in spread, sir. I hope
Okay.
there are different participants from across India, no? So I really thank you, sir, for this informative talk. I call upon Dr. Monica Chandramalar, madam, to give vote of thanks of this program, sir.
Thank you, sir.
Good evening, everyone. The best and beautiful thing in the world cannot be seen or even touched. They must be felt by heart among them. A very good evening to all the inquisitive mind gathered here in this forum to attend the day 3 session of the 7-day online faculty development program by the Department of Science and Humanities, Jeppiaar Engineering College. I consider it a great privilege to propose the vote of thanks to all the personalities who have witnessed it as a memorable and successful event. Today, my words are not enough to express the gratitude. On behalf of Jeppiaar Engineering College, I would like to thank our chief guest, Dr. V. Ganesh, CSIR Sikri, Karakudi, who graced us with this thought-provoking lecture on electrochemical biosensors for healthcare diagnostics. Also, we would like to express a pronounced gratitude to our dynamic and dedicated Director, Ma'am, Dr. Regina Jeppiaar, Chairman and Managing Director, Jeppiaar Group of Institutions, and a respected Principal, Dr. V. Natarajan, and a beloved Dean of Academic Affairs, Dr. Salisha A. Stanley, and a loving HOD, Dr. M. Merlin, for their constant encouragement and support to make this session a resounding success. Heartfelt and sincere thanks to our enthusiastic participants and the organizing committee members for their active cooperation. Thank you all for taking the time out for your busy schedule. Thank you.
Yeah. Thank you, sir. Thank you, ma'am.
Sir, thank you. Thank you, ma'am. Thank you, Sunil. Thank you. Thank you. Okay. So shall I leave now? Or?
Sure, sir. Sure, sir.
Okay.
Thank you.
Thank you. Thank you. Bye. Yeah.
Tony?
Regan, thank you, Regan.
Thank you. Tony, will you post the feedback link? Yeah, sure. Yeah, thank you so much, Tony. Yeah. Thank you, Tony, for your kind help. Yeah. Tony, from tomorrow onwards, we are going to use Google Meet. Huh? Yeah, okay. Almost 100 participants are there, no? So I think we can accommodate. Yeah, okay. No problem. No problem. It's a technical problem we may have. Yeah, it went on well. Tony, we have to hold. We have to hold on, huh, Tony? Yeah, sure. Yeah, okay, ma. Tony, I think today by 5:45 we can close, no, this feedback link. என்ன இன்னைக்கு ஒரு 100 பேர் தான் வந்திருப்பாங்களப்பா. Yeah, okay, 5:45.